So this is going to be a brief video in which we're going to talk about higher order derivatives and just formally define them. So this is something that I'm assuming you're all familiar with from calculus. We're just going to look at it with analytical formality. So let's say then that we've got some function that is a real valued function defined on our closed interval from a to b, so a subset of the real line. And we'll now say that this function f is going to be differentiable everywhere inside that interval, so differentiable on our closed interval ab. So that means take any point p inside this domain and the function will be differentiable there and will have a value for the derivative. We now want to talk about what it means for the function to be twice differentiable at a point p, what it means for it to have a second derivative at a point p. So because it's differentiable everywhere on the entire domain, that means we can now actually view the derivative as being a function. So a function on our entire domain, our closed interval from a to b, and it's going to be a real valued function. And the way this is going to work is it will map any point in that domain. So it'll take any x inside our interval ab, and it will just map it onto the value of the derivative at that point. So x is inside here, the function f will be differentiable there, it'll have value derivative there, which we've called f prime of x previously, and now we're going to create this function, this derivative function, that will map each point in the domain onto the value of its derivative there. Now what you can ask is this new function that's going to be defined everywhere, this is well defined everywhere because I've said it's differentiable everywhere, so everywhere will have a value for what the derivative is this new function, the derivative function, going to itself be differentiable? And if it's differentiable at some point p, then we would say that the original function f is twice differentiable at that point p. So let's write this out in full then. So for some p inside that interval ab, we'll say that f is twice differentiable, and I won't again, in fact I will. I was going to say I'll just abbreviate differentiable down to diff, but I'll write it out in full. F is twice differentiable at p. What this means is that the function f prime must be differentiable at p. So that means that the limit as t approaches p of f prime at t minus f prime at p over t minus p exists. That's the meaning of f prime as a function being differentiable at the point p. This is the difference quotient for the point p. And if that's the case, we will call the value of this limit the second derivative of the function at p. And we can further generalize this. So we can now say, suppose our function f is twice differentiable everywhere on the closed interval ab, meaning that it's differentiable everywhere on the closed interval ab, and then its derivative function is then differentiable everywhere on the closed interval ab. You can then define what it means to have a third derivative at a point p. It will be that the second derivative, viewed now as a function, is going to be differentiable at the point p. So writing this down, if it is the case that our function is twice differentiable everywhere, then we can now think of the second derivative as being a function, a real value function on the closed interval ab, where it will map any element x onto the value of the second derivative at that point. And we've said we're assuming it's now twice differentiable everywhere, meaning that there will be a second derivative value for all x inside this interval ab. So then, for it to be 3 times differentiable to point p means that this second derivative function will be differentiable at the point p. So again, the limit as t approaches p of the second derivative evaluated at t minus the second derivative evaluated at p over t minus p must exist, and we'll say that it's equal to, or denote it, f triple prime at p, the third derivative at p. And this goes on. If you then say, suppose your function is 3 times differentiable everywhere on the closed interval from a to b, meaning that it's differentiable everywhere on the closed interval a to b, its derivative function is then differentiable everywhere on the interval, its second derivative function is differentiable everywhere on the interval, then you've got a third derivative function that you can define on that interval, because it is going to have a third derivative at every single point inside that interval. So you can then define it as a function, and it will be 4 times differentiable somewhere if that third derivative is then differentiable at a point. And this goes on and on and on. And there are some functions, of course, that are going to be infinitely differentiable. You can differentiate them however many times you like, and the new function that you get will always be differentiable everywhere. So you can then continue on. So that's all I really wanted to say in this video. We will use these concepts of higher order derivatives in subsequent videos.